In this video, we will discuss the solution for the second order ODE. So far, we have learned that an electrical circuit consists of resistor and capacitor can be modeled by using ODE equation like this, where you have electrical source ET here on the right hand side of the equation. Let's assume that this electrical source is a battery with 9 volts. So you can represent this by 9. And you should know that I is equal to the current and charge is equal to the QT. We would like to know what is the change of the current or the charge with respect to time. We know that the voltage consumed by the resistor here is equal to IR, where the current I can be represented by dq over dt. So you know that this part is the voltage consumed by the resistor. The voltage consumed by this capacitor is equal to 1 over C multiplied with Q. If the value of the resistance and capacitance are provided, so in this case you have R equal to 8 and C is equal to 5, then by solving this ODE, we can obtain the solution for the charge as well as the current, where the I and Q are changed over the time. This equation is called ODE because there is only one independent variable, which is the T in this case. So you should know that for the independent variable, normally we have the time or the space to be the independent variable. Right? So in this case, it will be our time. So since we only have one independent variable, therefore this is known as ODE. And if you more than one independent variable, so in this case, it's called PE. Right? So this is not the case. And then if you look at the dependent variable, so you will find that the Q here is your dependent variable. In simple, dependent variable is something that you are going to solve. So you would like to know what is the change of the charge, which is Q over the time. The highest order of this ODE is 1, where you have the first derivative here. Therefore, the order is 1. So you have a Q prime is the highest order, followed by Q, which is equal to your right hand side. So if you look at the coefficient, so you see all of the coefficient here is constant, right? Which is 8, 1 over 5, and 9. So if all of them are constant, then in this case we say it's a linear ODE. So this RC circuit here can be represented by this equation, and from here we are able to tell that this equation is known as the first order linear ODE. Previously, you have learned how to use the integrating factor or the IF to solve the first order linear ODE, where in this case you need to ensure the coefficient for the first derivative here must be equal to 1. Therefore, you need to divide it by 8. So you should obtain 40 here, and this one is 9 over 8. Then you can obtain the integrating factor equal to exponential power of integration of the second coefficient here, which is 1 over 40. And then you need to integrate this coefficient with respect to the independent variable. So you should obtain the integrating factor to be this answer. So after you obtain the integrating factor, then you can continue with the step by multiply it to the left hand side and the right hand side, and then you will recognize on the left hand side here this format is exact, which can be further simplified by using this formula. So you can take the derivative of the integrating factor multiplied with the dependent variable. So your integrating factor is this, you can substitute inside, and then your dependent variable, so in this case is Q. So the right hand side component here should be remain. Then you can continue to integrate both sides. with respect to dt, and this term will be cancelled. And after you solve it, you should obtain the final. By using the integrating factor strategy to solve this first order linear ODE, then you should be able to obtain the solution in this format. So when you plot it, you obtain something like this, where the intersection here is equal to 45 plus c. So over here your t is equal to 0. So you substitute inside this equation, you also obtain the intersection to be 45 plus. So if you want to know what is the current, since we know the current is equal to Q prime, so you can continue to differentiate this to obtain the current. So differentiate 45, you should obtain 0. Differentiate this component with the exponential, then you need to multiply the coefficient here in front, and the exponential term remains. So if you plot the curve for the current, then you should obtain something like this, where at time is equal to 0, so we substitute t equal to 0 inside here, you should obtain the current is equal to 0. So the solution for the charge and the current that you obtain in these two equations is called the general solution, because you have unknown coefficient c here. If you use any arbitrary number for the c here, so for example, if you substitute c equal to 1 in this case, and then you substitute the q inside the formula, and you will still obtain a valid equation. So this means that you have the general solution. So to obtain the particular solution, then you must know the initial condition for this application. So for example, in this case, when the switch is open, the current at t equal to 0 is equal to 0 also. And also the charge is equal to 0 when the switch is open at t equal to 0. From here you can form two initial conditions that can be used to find the unknown c here. With that, you can solve the particular solution for qt and it. So when the switch is closed at t greater than 0, then you can obtain the corresponding charge and the current by using these two equations. So far, we have discussed the important strategy and concept to solve the first order linear ODE. For example, in this case, we use the RC circuit. So if we extend the problem by include the inductor inside the circuit to form the RLC circuit. So we know that the voltage consumed by the inductor here is equal to the inductance multiplied with the second derivative of charge. So for this circuit, the electrical source ET is written in the right hand side, and the voltage consumed by these three devices are given on the left hand side here. The highest derivative order is 2 in this case, and the coefficient L, R, C are all in constant. We have DC voltage in this case for the power supply, so which is given in constant. Therefore, we can say that this equation is a second order linear ODE. The strategy to solve the first order ODE previously cannot be used to solve the second order ODE here. To solve the second order ODE, first of all, you must recognize that the solution is comprised of two. One part of the solution is called the complementary solution, and the second part of the solution is called the particular solution, where the C is indicating the complementary solution and P is indicating the particular solution. So this is very important. Bear in your mind, if you have a second order ODE, like this case, so the total solution here, so in this case, you want to find the charge, which is Qt. So the total solution is equal to the complementary solution here, plus the particular solution. We will learn more how to find the complementary and particular solution later. In this example, you have LC circuit, which is comprised of the capacitor and the inductor. So the voltage consumed by the inductor and also the capacitor are given here, and the electrical source ET is given by this. So from here you can see this is second order linear ODE, where you are going to find the charge Q with respect to the time. So to find the solution of this, at the moment we know that this solution is equal to the complementary solution plus the particular solution. How if we have RL circuit where you have the resistor plus an inductor here? So this is the voltage consumed by these two devices, and this is the voltage input or voltage supply over here. From here we can see that the equation is in Q double prime plus Q prime. So this is second order ODE. Therefore our solution is equal to the complementary solution plus the particular solution. There is another alternative to solve this problem where we can reduce the order by let the I, which is the current, equal to the Q prime. So dQ over dt here is equal to I, and then if you differentiate I, you should obtain Q double prime. Therefore we can substitute Q double prime to be I prime here. So in this example you see that if you use a suitable substitution, you're able to reduce the second order ODE to the first order ODE. By doing this, we can simplify the problem. This can be solved easily by using the integrating factor approach that you learned previously. So we know that for the second order linear ODE, the solution consists of the complementary solution and also the particular solution. To find the complementary solution, you need to solve the homogeneous part of the ODE. So we know that this is the general format for the homogeneous ODE, where you have right hand side equal to 0. For example, in this case, you arrange the ODE in this standard format where you have the dependent variable y prime, y double prime, and so on the left hand side, and the remaining term you put on the right hand side. So in this case, you found that the right hand side is equal to 0. Therefore, we can say that this is the homogeneous ODE. We will learn the strategy to solve the homogeneous ODE here. So at the moment, let's assume the solution is provided, and the solution that you obtain from the homogeneous ODE is called the complementary solution, which is equal to YC here. So for this example, your YC is equal to this answer. For non-homogeneous ODE, your right hand side will not be equal to 0. For example, in this case, your right hand side here is not equal to 0. So this is known as non-homogeneous ODE. Later you will learn the strategy to solve the non-homogeneous ODE to obtain the particular solution. So assume that from here you can obtain your particular solution, but the total solution will be equal to the complementary solution plus the particular solution. So if you just provide the solution here, this is incomplete. You need to continue to find the complementary solution from this equation. Find the complementary solution, which is the YC in this case. You need to change the non-homogeneous into homogeneous ODE by let the right hand side equal to 0. So by doing this, if you continue to solve it, you can obtain the complementary solution. So if you look at this, these two are the same answer when you let the right hand side equal to 0. So in simple, to find the complementary solution, you need to let the right hand side equal to 0. To find the particular solution, you continue with the non-homogeneous ODE where the right hand side is not equal to 0. So your final solution to this ODE can be written in this form. So your YT, which is the dependent variable in this case, is equal to YC plus YP, where your YC is obtained by this, you can substitute, and this is your YP. So after you substitute inside, you obtain the final answer.